In this video lesson, we'll discuss the design and implementation of a software module for a temperature and humidity sensor. This sensor has an I2C interface, and we'll be making use of the I2C module from the previous lesson. You can see the topics here, and I'll just go through them quickly. We start with the requirements for this module, which are not very long. Then we'll briefly look at the theory of operation of the sensor by going through the data sheet. We just look at a small part of the data sheet, enough to implement our requirements. Next, we'll discuss some design decisions, and then the state machine design. Next, we'll look at the module API, which is a .h header file, and we'll look at some of the implementation, which is the .c file. Then I'll do a demo with the module, including showing a sort of nasty error case. And as part of this demo, we'll be using the logic analyzer. Then after a brief summary, I'll provide some prompts or questions for you to try to answer. For each prompt, I'll give you a second to pause the video if you want, and then give you my take on the prompt. So here are the requirements for the module. The module name is TempHum, which stands for temperature humidity. It's not a very clever name, but at least it's not too long. What the module must do is perform background sampling of temperature and humidity using a Sensorion SHT31-D part. The default sample rate is 1 second. It must do CRC checking of the received sensor data as supported by the part. A CRC is a method to verify the data is valid, and we'll be discussing this later. It must also provide a non-blocking GET API for the latest sample value and the age of the sample. So the idea is that at any time a user of this module can get the latest sample value. The module does not support making a measurement on demand, although that could be a future feature. Now it must support multiple of these sensors in the system, and these sensors might be on the same or different I2C buses. And then finally, it must provide test and debug support. And here I list the commands that I commonly implement for this kind of thing. We'll be using some of these commands as part of the demo. So I'll just pause the video for a second in case you want to read through them. So this is the data sheet for the temperature and humidity sensor, and this is where we will find the theory of operation. Now, I'm just going to show you a few things in this document that are relevant to the implementation of the TempHum module, and so I'll be jumping around. But I did read through this entire document myself, as I would if I were doing this work for my job, and I encourage you to look at it also. There are a lot of things that can be done with this sensor over the I2C bus that I don't cover in this lesson. So first, I'm going to go to Table 7, right here. This table shows how the I2C address is controlled by the adder input pin. If the pin is low, the address is hex 44. If the pin is high, the address is hex 45. Now, I have nothing connected to that pin, but the schematic of the Adafruit board shows a pull-down resistor. So the address will be hex 44. And as you can see here, the chip is not very flexible regarding I2C addressing, and this is how we can run into address conflicts. Now I'm at Table 8 on page 10, which shows the commands to do a one-shot measurement. We'll use one-shot measurements in TempHM. Now, the command consists of 2 bytes, the most significant byte and the least significant byte. First of all, you might notice that there are different commands for different levels of repeatability. When you're working with sensors, there are terms like accuracy, precision, repeatability, and others. These are important concepts to understand, but they're outside the scope of this course, so I encourage you to learn about them yourself. The command bytes also determine whether clock stretching is enabled or disabled, and we'll see how that works in just a second. So down here, you see some message sequences for sending a command and reading the response. So in this first line, we send the command. There's the address and then the 2 bytes of the command. And notice here is a start condition and here is a stop condition. So this is a complete transaction. Now what this diagram shows us is reading the measurement, and the assumption is that you will be reading it before the measurement is complete. So it starts by sending the I2C address, and then there are 2 cases, whether or not you have clock stretching enabled. In this first case here, you don't have clock stretching enabled. So what the device does is just knacks the address. And that sounds a little cold to me, but that's what it does. Anyhow, the idea is you would try again later. And let's say at this point the measurement is done. And so now it will ACK the address. And then it'll continue on to do the read. Now let's look at the second case where clock stretching is enabled. So what happens here is it does ACK the address, but then the device pulls the clock line low, which is known as clock stretching. The master will notice that, and it will just wait. And then when the measurement is done, the sensor will release the clock. The master, being the MCU, will notice that and will continue on. Now in the temp hum module, we actually put a delay after sending the command to attempt to avoid either of these scenarios. But just in case for some reason the measurement isn't ready, we choose a command that enables clock stretching, because clock stretching doesn't really require the software to do anything. The I2C bus hardware takes care of this clock stretching. So let's now go to the actual data, and there are 6 bytes. You'll notice there are 2 temperature bytes, there are 2 humidity bytes, and then for each of these pairs there is a CRC byte, which we'll talk about now. So here I am at table 19, which is on page 14, and this table contains information about the CRC calculation. So the idea is that you take your data bytes, run them through a CRC calculation, and see if the result matches the CRC in the message. If there is a match, it means that there is a very high probability that the data bytes are valid, that there was no error when getting the data over the bus. If the CRC bytes don't match, you definitely have a problem. So the CRC calculation is based on a lot of theory, and it's designed to detect as many error cases as possible. I won't go into that, but you might want to do some more reading on it. Now, fortunately, it's easy to find C code to compute CRCs and find this code on the web. The table sort of contains input parameters for that code, and we'll look at the CRC calculation code later in this lesson. Another key piece of information is how to take those raw data bytes and convert them into something meaningful. And these are the formulas to do that, both for the relative humidity and the temperature, either in degrees C or degrees F. These calculations look pretty straightforward. Now with embedded, you often want to avoid floating point. And so if you do these calculations with integers, you do have to be careful of the order of operations so you don't lose resolution. Finally, I'm at table 4 on page 5. This table contains the measurement duration for the different levels of repeatability. And you can see that the highest value is 15 milliseconds for high repeatability. So we will wait that long after sending a command to the sensor before trying to read the result. Here I discuss design decisions for temp hum, and there is really just one. And this one might be obvious, that the temp hum module will use the I2C module for communication with the sensor. I mean, why would have I written the I2C module if I wasn't going to use it? So what I'm doing here is highlighting the advantages of this layered approach. Now the big thing is the I2C module hides the complexity of I2C from the temp hum module. Next, the I2C module provides hardware abstraction and thus makes temp hum more portable. The idea is if we moved this software to another MCU, then the I2C module would likely need modification to support different I2C hardware. But this temp hum module wouldn't or shouldn't require change. Next, the I2C module allows sharing the I2C bus with other modules via this reservation scheme. So if we had a display with an I2C interface and that display was on the same bus, and if there was a software module for the display, like temp hum, then the two modules could each use the bus without being aware of each other. Finally, the I2C module has some test and debug features that would help during temp hum development and support. So here is the state machine for temp hum. As with the state machine for the I2C module, this is a simplified view and not all of the error transitions are shown. So I came up with this by just going through the steps of what is needed to do a measurement cycle. And what we do is send a command to the sensor, we wait a short time, and then we read the result from the sensor. Now if you remember, the I2C state machine events were largely based on interrupts. This is not the case for this module. Let's go through the events. So there is a start measurement periodic timer event. This is a timer callback and it tells us it's time to do the next measurement. All the rest of these events involve polling. And polling is a common thing to do in a super loop design, and if the polling overhead is low, it's perfectly fine. So the way we achieve polling in this module is that the super loop will be calling the module's run function. And each time the run function is called, the module will do whatever check it needs to do. So the outcome of calling I2C reserve is an event, as well as the result of calling I2C get op status. And finally, there is an event based on a simple time calculation where we are waiting for the sensor to perform a measurement. So let's see how this works. We start in idle, and from here the periodic timer expires that tells us to start a new measurement. This moves us to the reserve I2C state where, of course, we want to reserve the interface. So each time through the super loop, we will call I2C reserve. If it fails, presumably because there's another module using the interface, we stay in this state. But if we get the reservation, which is the success case, we then call I2C write with the command that performs a single shot measurement, and we move to the write measure command state. In write measure command, we call I2C get op status to check on the write operation. If we get an in progress result, we stay in the state. If we get a failure, we go back to idle. We'll try again next time. But we hope that we'll get a success. And in this case, we record the time, which is the beginning of the measurement, and we move to the wait measurement state. So in wait measure state, we calculate how long we've been there. As discussed previously, we should wait 15 milliseconds to be certain the measurement is done. When that time is up, we call I2C read to read the measurement data. So the read measurement value state is a lot like write measurement command, as we keep checking the status of the operation. And I'll just focus on the success case this time. In that case, assuming the CRC is good in the measurement data, we save the measurement value as the last measurement. And that brings us back to idle. And you might have noticed that before we return to the idle state, we always release the I2C interface. Now I'd like to say a few things about guard timers and error handling. Now in this state machine, I don't have any guard timers. As you might remember, the I2C module has guard timers, and I should be able to depend on those for any cases where we are waiting for an I2C operation to finish. Now you could say, I don't trust the I2C module and I'm going to have my own guard timer. That is engineering judgment, and it might be the correct approach where every module needs to look after itself. Another thing you might think about, the start measurement timer callback is periodic, and it will continue to expire even if the state machine is stuck. So if we get that callback event in a non-idle state, we will know we are stuck. So we could sort of use that as a guard timer, although the duration might be longer than what you want. Now, besides guard timers, there is the more general issue of continuous measurement failures. So perhaps there's a threshold on the amount of time without a successful measurement. The most difficult part of these questions is not how you implement the detection mechanism, but what to do when it happens. Let's look at some possibilities. You could print warning messages and keep going. No one's going to see that in the field. You could send an alarm to a management or monitoring system if applicable. Of course, a lot of systems don't have monitoring or management systems. To get a little bit more proactive, you could try to reset the sensor chip from your software and maybe reset the I2C bus. That might clear it up. And then usually the most drastic thing is you reset the MCU. And often the hardware design is such that this results in a reset of all the board hardware, including the sensor chip. Now, what we should do depends on a lot of things about what the product does, how important that temperature or humidity measurement is, and so forth. If you think this is a rare scenario, the board reset choice is often used because it's simple, and if anything is going to fix the problem, that should fix it. And we sometimes call that using the big hammer, or we might say go big or go home. So my experience is that you spend a lot of time on this kind of thing when working on embedded. Often more time is spent on this, it seems, than normal operation, because often there is not a clear correct answer. You might like this or dislike it, but it's part of working in embedded. So now let's look at the API for the temp hum module. And I'll just point out some key structures and functions. Here is the config structure for this module, and we specify the I2C instance ID, which is essentially like saying which bus the sensor is connected to, the I2C address of the sensor, how often we should be sampling the sensor. I believe this defaults to 1 second. And this is how much time should we give the sensor to perform the measurement. And I believe the default is 15 or 16 milliseconds. Here is the form of sensor measurements, and the measurements are in integer format, but we multiply them by 10, the values by 10 to keep the resolution. So this is the degrees C times 10, so if it were 20 degrees C, this value would be 200. And this is the relative humidity times 10, so if the relative humidity was 45%, this would be 450. Here are the core module interface functions, the standard form, and these are called from the module startup code and the super loop. And in particular, the run function is the one that's called from the super loop very frequently. In terms of other APIs, there's just one, and that's to get the last measurement value. And in addition to the last measurement value, this also returns the age of that measurement. So in other words, how long ago was it taken? You would expect that to be some value less than the sample time. If the sample time was 1 second, you'd expect this to be something less than 1 second. If it's greater than 1 second, it probably means the module is having some problem. So now we're going to look at the implementation of the temp hum module. And again, I'm just going to give a few highlights. So first, I'll just scroll down and we can see the states. These were the states in the state machine. And then this information, the data structure that holds the variables for each instance of this module. And so there are things like the configuration, the last measurement value, and so forth. Here's the actual state variable. So now I'm going to go to a particular line. And this is one of the core interface functions, and this is the run function, which is the one that is called from the super loop. So this will be called at a very high rate. And the bulk of the state machine is in this function. You'll see that it does a switch on the state, and then for every state it does whatever it needs to do per the state machine. So for example, in the case when we're in the reserve I2C state, it calls I2C reserve. If it succeeds, which means we have gotten control of that bus, then it does an I2C write and writes the measurement command to the sensor. And assuming that write succeeds, means the initiation was successful, then we go to the write mesh command. And you can go through the rest of this function, and it follows the state machine diagram, I think, fairly well. There's one more I want to take a quick look at, and this is the case where we're waiting for the measurement value, and we call the get op status. If it's successful, it means we have the measurement value. So this is doing the CRC checks on some of those bytes. And if those succeed, then it's doing the conversion of the raw data into temperatures in degrees C and humidity and percentage. So the last thing I'd like to show is the actual CRC calculation, which is 513 at the end of the file. And this code, and I'll show you the function, you can see it's not too small or not too big. This is not a very efficient version of the CRC function, but it is simple, and we're only doing a CRC over a few bytes, so it doesn't have to be that efficient. Again, this came from the web somewhere. You'll see copies of this all over if you Google CRC8 C code. And there are some parameters for this function that come from the data sheet. For instance, the polynomial is an example. So that's it for the implementation. Now I want to do a few demos of the temp hum module. What you see here is the same setup I had before with the I2C module. The logic analyzer is on top and the MCU console is on the bottom. Now the temp hum module is taking samples every second. So if we enable the logic analyzer, we should soon get a trigger. And there it is. And if we look at it in this tabular format, we can see a start here, and there's 2 bytes of data transferred. That would be the command. And then 16.7 milliseconds later, we do another operation, and we read 6 bytes of data, and that's the measurement result. So we've seen this same thing really in the I2C demo, but let's just look quickly at these the signals. There is the write, and here is the read, and nothing too special about those. Now what I'd like to do is reduce the amount of time that we wait before we read the measurement. As you might remember, if you read the measurement or try to read the measurement result too soon, we have chosen an option where the chip will stretch the clock. And so we have a temp hum test command that allows us to do various things. And so one thing it allows us to do is change that measurement timer, the wait timer. So I'm going to do a temp hum test measure time instance 0, and it was, I think, 16 milliseconds. I'm just going to make it 10. So now, if we get another trigger, here is the right of the measurement command. And then if we look at the timestamps on here, we'll see that about 10 milliseconds, well, 9.8 milliseconds later, we start to do the read. But then you'll see a gap in time here. There's about 3 milliseconds gap. And so let's look at that read operation. So here it is. Here is the address being sent. And the next thing that should happen is we should start reading the data. Well, what has happened is someone is holding the clock down, and that someone is the sensor chip, because it's doing this clock stretching while it finishes the measurement. And if we keep going here, it's holding it down, it's holding it down. I'm just going to jump straight to it. So here it was holding it down. Finally, it released the clock. So now the master can continue going, and now it's reading the measurement data. So that is a rather long clock stretch of 3 milliseconds, but it is part of I2C, and it did its purpose here. The other thing I'd like to show you is the CRC calculations. And in this test command, I also have a test where you can provide data and it will do the CRC. So what I am going to do is do test CRC8, and if we take these 2 bytes of the humidity data, 0x8f, and this one is 0x98, and compute the CRC8, the answer is 0xbb, which hopefully is this, and it's not. What did I do wrong? Oh, that's not 9.8, that's 9b. Let's try it again. Temp, well, here. This is a lot easier. 9b. Okay, now the result is E8, which matches this, E8. Good. So that is the CRC function that will, helps verify that there were no errors. And you saw it at work here. I put in the wrong byte and the CRC did not match. Finally, I'm going to show you something that I came across that is not so nice. I'm first going to stop temp hum from taking measurements. And the way I do this is by reserving the bus, and that'll block it. So we can do an I2C test reserve instance 0, and that worked. So now let's try to read a measurement result without first giving a measurement command. So I'm going to start the analyzer, and I am going to do an I2C test read instance 0 address 44, and we want to read 6 bytes. Well, let's see what happened. We don't have many bytes here. If we looked at what happened is, here's the address byte, and it looks like the sensor is stretching the bus, or stretching the clock. However, if I start tracing again, that signal is still low. It's stretching it forever. So we're now in a situation where the clock signal is being pulled low by the sensor chip, and there's no way to get out of this. We cannot communicate on this bus. I mean, if I try to do another read, just to show you what would happen, we get return code -7. Actually, I should then do an I2C test status 0. So this -7 means there was a peripheral error, and if we look at in the I2C header, error 2 is bus busy. So we're stuck. Now, the only way that I can cure this is to reset the sensor chip. And I'm going to do that right now on the fly by just grounding the reset pin. And there I did it. And so now the clock is back. And now we can, I'm going to release the bus, release 0, and did I, no, type it, I2C test, oh, release 0. Okay, and there we go. So I released the bus, and now things are back to normal. We did a successful measurement. Now, you could argue that, well, tough luck. You didn't issue a one-shot measurement command to that sensor chip, so when you tried to read it, you know, it did what it did, and it's your fault. And okay, I sort of accept that, but it's still not very nice. If I were using this sensor chip on a product, I would put a lot of thought into this, because in software systems, things happen. And especially software systems that run 24/7 for days and months, you know, things happen and you don't want to get stuck like this. So if I were putting this into a product, I would think about how from software I could recover from this condition without having to maybe even reset the MCU. Resetting the MCU would be one choice if that resets the other hardware on the board. Another possibility is I have a GPIO connected to the reset pin of that sensor, and that way I could reset that sensor on its own. But it is always good to try these things and try odd things and see how these devices behave, because you'd rather know early than find out about it late. Now, so far we have looked at the messages on the wire, but have not actually seen the temperature and humidity values. So we need to look at those. So there are two ways to get those. One is I have a test command option to print the last measurement. So temp hum test, and it's get last measure. So temp hum test last measure and instance 0. And so there you see 22.4 degrees, 49.7% humidity, and there's the age of the measurement, which is 885 milliseconds. And remember, we're doing a sample each second. The other thing I can do is I have a log statement that prints out the measurement value every time a sample is done. And so let me enable the logging. And so there you see, once a second, we're printing it. And in this case, it's printing the value in raw form. So those numbers are should be divided by 10. You can see that the humidity is changing a little bit. The temperature is pretty constant at 22.4, or there it went up to 22.5 degrees C. So there it is. It is doing what it is intended to do. So here is a short summary of this lesson. Use of the generic I2C module simplifies the implementation of the temp hum device-specific module. And it also provides other advantages such as simple sharing of the I2C bus. A state machine was again used to orchestrate a sequence of I2C transactions to perform the measurement task. This sensor device used CRCs to verify the integrity of data transferred across the I2C bus. And the demo showed us that it is good to experiment with I2C devices to see how they respond to unexpected I2C read and write operations. Murphy's Law says that anything that can go wrong will go wrong. So you need to think about the need for recovery mechanism if a device, in the case that a device gets stuck in some bad state. Here are the prompts for this video lesson. I'll pause here for a few seconds in case you want to pause the video and look at them as a group. On the next set of slides, I'll go through the prompts one by one and reveal my take. If you had two SHT31-D sensors with the same address on a single bus, how would you likely detect it? Well, the measurement data will likely be corrupted, assuming the data sent by the two sensors is not exactly the same, and we saw how that worked in the last lesson. And if the data is corrupted, you will very likely get a CRC failure. Per the data sheet, what are the 3 ways to reset the sensor chip? Well, there's a soft reset, which is actually an I2C command. We haven't looked at that command, but it's something we could implement. You can pulse the N reset pin, and that's actually what I did in the demo when we got that chip where it was holding the clock signal down. Or you can power cycle the chip. What is the recommended method for resetting the chip, the sensor chip, that does not involve removing the power supply? What do you think is the reason for the choice? And again, this is from the data sheet. Well, the recommended method is to pulse the N reset pin and not to use the soft reset. And pulsing the N reset pin is more reliable than the soft reset because it doesn't depend on I2C communications working properly. And this again is what we saw during that demo. Per the data sheet, does the sensor chip support any combined format messages? Well, the answer is yes, it does. And the thing to look for is an I2C transaction with more than one start condition before the stop condition. And that means it must be combined format. And I believe they're all write followed by a read. So the 2 examples I saw were the fetch data command, which is in table 11, and the read status register command, that is in table 17. Well, this is the end of the lesson. I hope you found it useful, and thanks for watching.